Howdy students, this is a lesson on periodic trends. We're going to cover multiple trends today, so it's important to have your flip books out and make sure you pay attention to which page number you're putting these on. Our objectives today is to look at reactivity patterns using ionization energy, effective charge, and atomic radius. We're going to use these models to explain the formation of ions or group charges, and then we're going to use the trends to explain chemical properties of elements. The first trend we're looking at today is atomic radius. Atomic radius is defined as 1/2 the distance between the nuclei of two atoms in the same element. So if we're looking at these two bromine atoms here, what we're going to see is that we're looking at the nucleus of one and the nucleus of another, and essentially that's 2 times the radius. So if we half that, that would be the effective radius distance from here to here. Okay. So basically what we're looking at is the size. That's really the trend we're looking at. How large are atoms? And we know that as we go down the periodic table, the energy levels, 1s, 2s, 3s, they get bigger. This is influenced by the trend we learned last week, Zeph, because nuclear charge increases from left to right. We know that the protons pull on the nucleus a little bit more, bring the electrons closer, and we're actually getting smaller as we go from left to the right. So the greater the pull on the nucleus, the greater the Zeph, increased Zeph, the smaller the atom. So if we're looking at the periodic table, we already mentioned it, but as we go down the periodic table, the size increases because of energy levels. More energy levels, more distance, larger radius. As we go left to right, again, we're increasing the Zeph, so we decrease the size because the pull on the electrons is greater. So let's go to page 2 of your flip book. Go ahead and go to page 2 of your flip book. Let's look at the trend. Atomic radius increases from right to left and from top to bottom as we go down a group. So in your flip book, I want you to label the arrow. Go down and from right to left. If you want to go ahead and circle and put a star on Big Frank, he is the largest atom that we have on the periodic table. He's in the 7th energy level, 7s. And he has the smallest Zeph, effective nuclear charge, in that column. The smallest radius would be helium. It's not the one with the fewest protons. In this case, it just has the smallest energy level, 1s, and it has a greater Zeph than hydrogen. So this graph, if we were to plot all the elements, what we would find is that as we increase in atomic number, there's definite trends, there's definite pattern as we go from left to right, increasing atomic number. So let's practice. Place the following elements in order from smallest to largest atomic radius. So smallest over here and largest, small and large. So smallest, if we're looking at the periodic table, the one that's up and to the right would be the smallest. So I think carbon is up and to the right. You can take a look at your periodic table. And then after that, I believe it would be bromine. And then we go far, far to the left with calcium, and then radium. Aluminum, sulfur, chlorine, francium. Well, we know francium is the biggest, so francium is going to get the largest. And then I think for smallest, the furthest up and to the right would be sulfur, and then chlorine, and then aluminum. Which elements of the pair would have the smallest atomic radius? So basically, which one is up and to the right? Iron or cobalt? Silver or gold? Oxygen or sulfur? Feel free to pause and take a look before answering. Okay, let's keep moving on. So we're looking at cobalt and iron. Cobalt is further up and to the right. Silver or gold, well, silver is further up. Oxygen or sulfur, oxygen sits on top of sulfur. Okay, next trend, atomic radius, ions. So how do ions factor in? Well, there are 2 words that we want you to write down in your notes, okay? And the first one is cation, the second one is anion. Cations lose electrons. So essentially, if something loses an electron, we're going to take on a positive charge. So think about it. You have sodium. If it loses 1 electron, What's left over is a sodium that carries a positive charge. It has the same number of protons, and now it has one less electron. So this gets smaller. So cations get small. Anions gain electrons. So think of chlorine. It is going to gain one electron to become chloride, Cl-. So anions, negative ones, get bigger. Explaining ion size. So let's look at these images. Here's sodium. It's going to lose its valence electron right there. When it does that, it goes from a 3s down to a 2p. It gets smaller. Fluorine, it gains one electron, and it fills in right here in this missing spot. Has the same number of protons in the nucleus, so this gets bigger. The picture doesn't really do justice, but it does get larger. Okay, so is there a trend? Well, here's the trend. Let's go ahead and label metal atoms, metal, keyword metals, things in group 1, group 2, maybe even group 3 on the periodic table, they will lose electrons to become cations, which are positively charged. Non-metals will tend to gain electrons. These are things in perhaps group 5, group 6, and group 7. Therefore, these tend to get bigger. So cations get smaller, and nonmetals tend to get larger when they form ions. Our next trend is going to be ionization energy. Okay? Our next trend is ionization energy. So ionization energy, by definition, is the energy required to remove the outermost electron from an atom. Specifically, outermost, so we're looking at valence. If it has a greater Zeph, a higher pull on the electrons, it's going to take more energy to remove an electron. If atoms have electrons that are closer to the nucleus, then there is a stronger pull. Thus, it takes more energy to break the attraction. Smaller atoms with fewer electrons, so here's the pattern, smaller electrons with fewer electrons will want to hold on to them and have a high energy for ionization. Larger atoms do not want to hold on to their valence, and so there's lots of shielding from core electrons, and we have a low attraction, which means a low ionization energy. So that's a lot of explanation. Let's look at the periodic table. If we're graphing these energies, you'll see that clearly we have a low energy on the left side and a very high energy on the top right. So let's go to page 4 in our flip book, and let's draw these arrows. We're going to draw arrows to the right and up, and we're going to make a note that helium is our highest value, while francium, you can't see it on here, francium would be our lowest. And that's really what you need to know here for the trends. Sure, are there some exceptions? Yeah, if you're looking at zinc to aluminum here, or cadmium to gallium, there are definitely some exceptions here. You'll notice nitrogen drops to oxygen. That's more of an advanced level topic. So if we're plotting all of the elements, you'll see that the noble gases sit atop all of their groups. This is because they have the largest Zeph in each of the rows. You'll notice that the bottom elements will be the group 1 elements. They have the lowest Zeph in each of their rows. So which elements in each pair have the lowest ionization energy? Sulfur or phosphorus? Well, sulfur is up and to the right more than phosphorus. So phosphorus will have the lowest ionization energy. Chromium versus zinc. Zinc is further to the right. So zinc is going to have, I wrote that wrong. Zinc is going to have the higher, which means chromium will have the lower. Beryllium or lithium. Lithium is further to the left, so it is going to have the lowest. Place the following elements in order of largest to smallest. Large to small. So largest ionization energy would be furthest up and to the right. So if we're looking at zirconium, we're looking at phosphorus, we're looking at aluminum, and we're looking at cadmium. Okay? So zirconium would have the lowest. or the smallest value, because it's furthest to the left. Zirconium, and then we have cadmium, and then aluminum, and phosphorus is furthest to the right. Tin, lead, mercury, and arsenic. Feel free to pause so that you can work on this. So arsenic is going to have the largest. It is furthest up and to the right. And then we're going to have tin, and then lead, and then mercury. Okay, the next couple of trends here are electron affinity and electronegativity. You'll recall this was on page 5. We scratched that to make way for nuclear charge. So essentially we're going to be combining both of these into the same page today. The energy change that happens when an atom gains an electron. So in chlorine wants to gain an electron, there's going to be some energy that is released. This is influenced by the nuclear charge because there's a higher nuclear charge once we gain an electron in groups 16 and 17. The more affinity an atom has, the more negative value it will become because atoms who want electrons will release a greater amount of energy. And anytime we're releasing energy, we associate that with a negative value. So affinity or likeness is also related to electronegativity. So if electron affinity would be between just an atom, electronegativity is inside of a compound, which we haven't really gotten to yet, but they are connected. This has to do with the number of valence electrons in the row that it's in on the periodic table. Now, one thing to note is that electron affinity does not apply to noble gases, nor does it with electronegativity. Noble gases have a filled valence shell. So let's look at the periodic table. Let's go to page 6 in our periodic table, our flip book, and let's make note that the arrows go up and to the right. The highest value for electron affinity and electronegativity, even though it's negative, is fluorine. Make a note. We are not going to look at the noble gases. You'll notice all these values are 0. So I want you to scratch out that column, that family in the periodic table. Electronegativity, you'll notice, has the same trend. If we go up and to the right, so to the right and up, fluorine is the highest. And you'll notice the noble gases aren't showing up. So they're both directly related. Now, are there some exceptions? Perhaps. But for the most part, as we decrease metallic character, we increase in electronegativity. If we graph all the elements, we'll notice a similar pattern. We will increase electronegativity until we get to a new energy level. And then once we get into the F block, you'll see that things kind of level out. This is because there's so much shielding happening in the core electrons. So, which elements in each pair have the highest electron affinity? Iodine or fluorine? Well, fluorine, we know, has the highest. Iodine is lower on the table. Boron or barium? Boron is way further up and to the right than barium. Aluminum or chlorine? Chlorine is further to the right. The same trend would exist for electronegativities. Place the following elements in order of smallest to largest. We have platinum, tungsten, radium, iodine. So radium would be the smallest. And then we would have either platinum or tungsten. Let me check my periodic table. Tungsten is next, and then platinum, and then iodine. Calcium, boron, selenium, and oxygen. Calcium is furthest to the left. And then you have, now this one's tricky. Let's look at boron and selenium. Boron and selenium exist about here on the periodic table. Selenium is 2 rows down, and boron is 2 rows up. So when you have a tie like this, selenium's going to lose, and boron is going to win. And then oxygen is still furthest and to the right. Okay, group charges and representative elements. Recall that representative elements in the same group family will have the same amount of valence electrons. This means that elements in the same families will lose or gain the same amount of electrons in order to get to 8, the magic number. So, typically, if we're looking at losing or gaining electrons, we mentioned that metals form cations earlier, and those tend to lose electrons. Nonmetals form anions, and those tend to gain electrons. These will become positively charged, these will become negatively charged. So let's go to page 3 in our flip books, and let's find the periodic table and write in the number of valence electrons. 1, 2, 3, 4, 5, 6, 7, 8. We're going to skip the D block because remember, they're in a lower energy level. But what about losing and gaining electrons? Well, it's going to depend because what we have is the ability to either lose or to gain up to 8. So, in the same page 3 in your flip book, above the valence electrons, I want you to write a +1, or in this case, 1+ above the alkali, a 2+ above the alkaline earth, a 3+ above the boron group, and then the carbon group, I want you to skip. Skip the carbon group. These can be plus or minus 4, and we typically don't look at these when forming ions. Can they? Yes. Will we look at them? Probably not. Nitrogen group, I want you to write 3-. Now we're going to start to go down. We're going to start to gain electrons. We're going to gain 3 electrons to become negative. We're going to gain 2 electrons. We're going to gain 1 electron. And then the noble gases, I want you to scratch out in your periodic table. There are no charge. You can put a 0 there if you'd like. No charges in the noble gases. So let's look. Given the number of valence electrons and group charges of the following atoms, beryllium is in group 2. It has 2 valence electrons. It's going to lose 2 to become 2+. Sulfur has 6 valence electrons. Instead of losing 6, it's just going to gain 2 electrons, and it's become 2- because remember, electrons are negative. Aluminum has 3 valence. It's going to rather lose 3 to become 3+. Argon is a noble gas, so it's going to have no charge. Hydrogen has 1. It's going to lose 1 to become a +1. So if we look at all the trends, we have metallic character, what we covered on day 1 of notes for experience 2. And then for experience 3, we covered a lot here today. We covered ionization energy, we covered atomic radius, we covered electron affinity, and what's not on here would be electronegativity.